astronomy through amateur activities. He was about 8 years old when his parents took him to star parties. And those included the Mount Cobalt Star Party, shown here on the right, and the Merritt Star Quest, a party held in the town of Merritt, British Columbia, population 2,700, shown at left, above the selfie of Ronan at Big Bend here in Texas. He says that he chose UT because of the size and the diversity of its faculty, which supports his interests in star formation and the processes of young stars. He also was attracted by the McDonald Observatory. No surprise there either. Pre-COVID, Ronan was avidly engaged in public outreach. Right now, he's leading an effort to deliver lessons and other support and resources from UT astronomy into the underprivileged and low-income elementary and high school classes in our area. So please join me in extending a warm welcome to Ronan P. Kerr.
Yay. Hi, everybody. Thank you very much for having me. All right, let me share my screen and let's get going with the presentation here. Okay, so I'm very excited to present to you some of the very interesting, at least I think, very interesting work that I've been doing at UT Austin regarding understanding stellar populations in the solar neighborhood and their star formation history. So this is at its most fundamental level a story about understanding star formation. So let me start by going into essentially justifying my existence and saying, okay, so why do we want to do research into star formation? And it really comes down to the fact that almost everything that is visible in the universe has something to do with stars. You know, you look up at the night sky, there are stars everywhere. If you got a telescope, you can see some galaxies, or if you really know where Andromeda is, composed of stars, emission nebulae like the Orion Nebula shown here. Those are places where stars are formed. So understanding how star formation progresses really is a matter of understanding the backbone of how the observable universe is presented to us. And so obviously I'm not going to be doing like exactly that whole, I'm not going to be trying to like, you know, do all of that in this one project. But in my case, my goal is more specifically to understand the mechanisms that take place to advance star formation. So let me start by just briefly going over the ways that star formation can be done, and then how exactly I take this and do something new with it. So one of the most common ways to do studies in star formation is by observing star formation as it happens. This is looking at gas dynamics and looking at the stars that are being actively formed in these regions. So, you know, you could have very detailed studies of gas by using these radio, these millimeter, these infrared observations of these molecular clouds. And then you can observe the velocities of this gas as it goes in towards stars and as it accretes on to create protostars, to create planetary systems. It's a very fascinating way to do observations. And it's one that this is actually where I got my start in astronomy, was doing studies of that variety. But the problem with using this sort of a method is that it gives you a snapshot in time. So you're only able to observe, you know, the gas and the stars as they currently are. But if you want to trace back a star formation history, it's difficult to do that. So this is where stellar populations come in, which can be used to reconstruct a history by age-dating stars that span, you know, hundreds of millions of years in age. So that's what I'm going to be doing. If the title probably gave that away, but just to summarize exactly what we can do with this. So since we get a full history of star formation in a region, what we can do is there are a few things that we can do. So first of all, we can better investigate processes that happen very slowly. So if we have a slow progression of star formation that takes place over a period of, let's say, 25 million years, then if you are only observing using the gas and the actively forming stars, you're only going to be able to get a very tiny portion of that. But by observing populations, what you can do is you can observe all of those populations at once and then age date them and trace them back. And also, because of the fact that we have, a 30 million year roughly, you can probably go up to 50. We'll get to that a little bit later. But since you have such a long period of time over which you can observe these stars, you can also detect processes that are small and fast. So ones that wouldn't necessarily catch if you were only looking for gas, because they form and then they disperse. And what we can also do is more precisely look at the start and end times of star formation by looking at the ages and the distributions of stars and try to say, okay, this is when this star formation event ended, this is when this one began, this is the link between them. There's a lot that you can do by taking this sort of approach. So let's start with the sort of picture of star formation that we might typically think about. So often what you imagine in star formation is you have this big cloud of gas with all these pretty colors, and then it collapses and forms stars, and the result is something like you see on the right here with an open cluster that looks really pretty in a telescope. But that isn't actually typically the case when you're dealing with young stellar populations. Often, at least in the vicinity of the sun, what things look like is more like this. So not very exciting, but this is basically just clumps of gas and dust that slowly over time collapse to form stars. And you can imagine that if you have this sort of sparse environment forming stars, the result of star formation isn't going to be that beautiful cluster. It's going to be something like that. So I'm actually pointing directly at an association that was found as part of this project in that picture, and you're not seeing it there. It completely blends in to the background. So that's a challenge, and it's one that you have to overcome when you're doing studies like this. So let me just briefly explain exactly what that is. So the results of these sort of like lower density star formation events are called associations. And associations are basically the gravitationally unbound equivalent of clusters, which have much more gravitational binding to them. And as a result, these survive for quite a bit longer. So normally when you look for, or at least historically, how people first identified associations was there being too many O or B stars. These are these hot blue stars that don't live for very long. And the reason that you can identify OB associations, the reason that the O and B stars are where the young stars are is because if they were any older, they'd be dead. So they only live for tens of millions of years. Once they die, they are gone, and so therefore, if you're going to see them, they have to, by definition, be young. So associations are very dispersed, don't form clear overdensities, so we need to be clever in trying to identify them. And this comes to probably the least exciting part of my talk, where I try to explain how I identified young stars using data available to me. Okay, so there's a nice way to identify young stars, and that is because as stars are collapsing out of the molecular cloud, they are bigger than they would be at their final state. And their temperatures aren't actually that different during this process. So what ends up happening is you have stars that are like really bloated, but their temperatures are the same. So, the amount of flux scales with the surface area over which the light is being emitted. So stars are a lot brighter early in this process. So you can see here at your 1 million year mark, that's quite a bit brighter than at your 100 million year mark, and vice versa. So basically the idea here is if you know the basically color and the magnitude of a star, then you can learn a lot about, you can basically place it on this diagram and make an inference about what its properties are. Now, there are a few tricks to this. And the next difficulty is that not all stars that are, here on a, not all stars that are here on a color magnitude diagram are young. And that is because there are other ways to sort of like trick you into thinking that they're there. Like, for example, them having a binary. And if there's a binary, obviously that's going to make it brighter too. That is like a binary that you can't see with the telescope. So you need to have a way of sort of like trying to get rid of that. And we'll get to that in a minute. But in the meantime, the way that we get all of this information about about the magnitudes and colors of these stars is using Gaia. So Gaia it's an incredible spacecraft. Probably over half of the research I have ever done has been directly as a result of Gaia. Basically, it's been constantly surveying the sky over the past few years. And it's been getting excellent information on both the photometry, so that is like the brightnesses of the stars in different color bands, and also on the motions of stars. So that is both the proper motions, which are just like the motions of stars around the galaxy, but also the parallaxes. And this is basically, it's sort of like imagining like you look at your finger and you blink your eyes, the location of your finger relative to the background changes. And it's sort of that same idea, but with the Earth and the star. So that gives us distances to these stars. And if we want to figure out how bright a star really is, what we need to do is we need to put the distance and the magnitude together, and that makes an absolute magnitude, and that gives us the information to put it on that diagram. All right, so what we end up using here, so I mentioned that there are difficulties in having stars act like they're young when they really aren't. And the way that we do this is using what's called a Bayesian approach. So I'm going to summarize this in the easiest way that I know how. So imagine that we have Gaia stars. So these are stars from the Gaia catalog. And the information that we have on them is we have a brightness and we have a color. We don't have masses, we don't have any ages, we don't have any of that useful information that we might want to know. But then what we can do is we can, using our knowledge of what the solar neighborhood looks like, we can make a model that has stars with all of those properties. And then what we can do is we can say, okay, we got a Gaia star right here. Just to very broadly oversimplify this, there are 10 stars near to that point. 8 of them are young, 2 of them are old. Therefore, there's an 80% chance that the star is young. That's basically the idea that we're going for, is we're comparing each Gaia star to a model, and we're using that to infer a probability that that star is young. So this can basically allow us to construct a probability distribution as a function of age, and that can allow us to essentially set a probability that a star is young. So the way that we generate the model, there are a few factors that go in that could trick us into thinking a star is young when it really isn't. So mass, age, metallicity, so like amount of heavy elements that are in the star, multiplicity, so whether there's a binary companion that's unseen. We plug those into what are called, it's an isochrone set. It basically just generates sample photometry from star properties. And then we add reddening, because reddening is another thing that's problematic, and it is different everywhere in the sky. So we use these Lalama et al. Maps from it's a team in France that does some great research on this sort of thing. So we applied those reddenings to our model, different for each star, and then we were able to generate a probability for each star that it was within some threshold that we want for a star being young. This is what that looks like. So stars that are the most burnt orange on this side are the stars that we recognize as being likely young. We get 30,000 of them, and these have probability greater than 10%, that the age is less than 50 million years. You can see that these are mainly stars that are actually fainter than the sun. So it might be a little bit of a bizarre thing to think about when it comes to research, that we're having a better time identifying faint things than bright things. The reason for that is that another thing that can trick us into thinking a star is young is it being right here, which definitely there are young stars there, but there's also giants or subgiants. So we can't really confidently say if anything here is young, because subgiants happen to be pretty common, so they sort of look like each other. So, and what we can also do is, from the probability distributions that we generate using this Bayesian approach, we can also generate age estimations for each star as well. Okay. Now, this is just a nice little check to make sure that we're doing things in a logical way. So the top line here is for Taurus, which is a 5 million year old region. And you can see that we're getting, so this is basically the like star spectral type. The sun is here. Stars that are fainter are over in this direction. We're finding basically everything in the bar that is fainter than the sun. And as objects get older, our recovery rate goes down, but that's to be expected because, we're looking for things that look young. And as things get older, they look less young. So, it does degrade as we get up to the, 30 and 40 million year mark. But all in all, it still gets us a lot of stars that we can use for studies of stellar populations. So this is what happens when you take those 30,000 stars, you just plot them basically as a top-down view of the galaxy. And this is what you get. And you can see that there are a lot of features that show up here. So you got all these little, you got all these little clumps, and most of these turn out to be associations. So exactly what we're looking for, but not all of them. I circled one here. This looks like an overdensity, but it turns out that the stars in that overdensity have no commonalities with them in terms of motion. So if you have a real association, that gas cloud is moving in some direction, and the stars that are formed out of that gas cloud retain the velocity of that gas cloud. So if a star is really a member of an association, it's going to have similar velocities to the stars around it. This doesn't. It turns out that this is just a reddening anomaly. Nothing we can do about that. The Lala et al. Maps aren't perfect, so there are always things to be aware of that try to fool our results. But the bottom line is that when we recognize structures, so these structures that we're going to use to understand progression of star formation, we need to include both spatial and velocity coordinates to cluster stars. So now let's look into how we identify structures. So we've got this algorithm called Hdbscan. It's basically an algorithm that looks for overdensities in any data set. And it's a really cool algorithm because basically what it does is it doesn't have any sort of, it uses very few assumptions. So the only assumptions that you put into it are like the minimum size of the cluster that you want and a little bit of a smoothing parameter. Aside from that, you just let it go and it'll look for overdensities in whatever way you want. And the nice thing about this is that you don't really presume anything about the cluster. You don't think that it has any properties, and that's good from a scientific perspective because you don't want to, if you look for something, you're going to miss things that don't look like that thing. So this is a great way of preventing that from happening. Now, I'm not going to go into too much depth on exactly the nature of little details of the clustering that we use, but I should note that there are ways to do like different levels of this. So I limit fragmentation at the top level, and then I allow it to fragment farther down. So not going to get into too much depth in that. If you want to know more about it, feel free to ask me questions later on. But for now, let's get into what this result is, which this is where things start getting interesting. So this is looking at the distribution of these young groups that we identify as a function of galactic coordinates. So here is the galactic equator. Galactic center is right there. And you can see that we have a whole bunch of populations that are strewn out across our map here. This one here is the Sco-Cen Association. That's the very big one. This is Orion. This is Taurus in orange here. This is the Alpha Persei cluster. Perseus. So you can see that we find a decent number of different populations strewn across the sky. And things get, you start to see the structure in things when you go out to the top-down view of the galaxy. So here's the sun, and then we have these branches of young populations spreading out around the sun. So we've already got this very interesting view of stars in our solar neighborhood. And this is where we can start looking at, okay, what structures are known, which structures are not. And there are certainly ones that are known, like here, 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 etc. But there's also a lot that isn't. So excuse me. This one here, here, and here. These were all clusters that have only been recognized as part of very large surveys within the last year. And then this, and this are completely new. So no recognition whatsoever prior to the work that we've been doing. So we're already doing a better job than anybody else previously in identifying young stars. So, so far, so good. And it's also probably worthwhile saying that things like Aquila East, Lyra, Fornax Horologium, these are all smaller groups than we've really recognized up until this point. So we haven't really gotten into doing much with these groups yet, but it might be interesting to look into the longevity of these star formation events and see if we can trace these back to their origin locations and try to understand some details about their formation. But for the purposes of this talk, I'm going to be focusing more on these larger groups and understanding the progression of star formation in those groups. So this is basically restating what I just did. Now, last thing, in order to do a study of star formation history, you need to have information on where the stars are, but you also need to have information on the ages of each of the subgroups that we recognize with Hdbscan. So I mentioned that you can do this using the probability distribution from our Bayesian approach. That works well for individual stars, but the problem is that because our algorithm looks for things that look young, by definition, if there are some objects that we do not detect using our method, they are going to be the ones that look older, which is going to skew our result in terms of age. So we sort of like have to reintroduce stars that we missed by just looking for neighbors to the previous stars and then fit that result. And a result is shown here. So the ones that are that were recognized originally are all along this area here, along the top edge, but there's also some contamination. So this ends up striking a good balance by de-weighting members that are farther out and removing objects that look like they're binaries.
Excuse me, could you say what's on the axes there?
Oh yeah, sure. Sorry. This is it's a similar diagram to the model populations that I showed you before. So this is color and this is magnitude. So yes, sorry, I'm using rather paper. I'm using diagrams for my paper here, so it's a little bit more difficult to understand. But anyway, so now we're into the part of the presentation that I personally think is a lot of fun, and this is looking at the regions that we recognize and we're able to understand. So I'm going to start with a few that are basically test goes at the sort of results that we get, and then we'll go into places where we really think we found some very, very cool processes. So starting with Taurus here. So the known extent of Taurus is a series of long filaments that are currently forming stars up in this area. So that is groups 10, 11, 8, and 9. These are all locations where we have very active knowledge of current star formation. And then there are a few locations that are also around here that are that are known, but they haven't been linked to Taurus before. So that is groups 1, 7, and 6. So what we end up doing is by using Hdbscan on our population, and our population is very good at detecting these very fine links between stars. So this is your on-sky densities here. You can see that between, like 1 and 3, between 7 and the rest of these, you get these very subtle links of stars that connect them. So this is great evidence for, there being links between these populations that are known and these older populations. This has actually been somewhat contentious in the past, as in 2017, my current supervisor wrote a paper basically claiming there are large populations of older stars in Taurus. And then another paper came out the year after saying, no, there aren't. Those aren't really Taurus stars. You're all wrong about this. So this is a great exercise to sort of show that there are links connecting these. And beyond that, we also find some groups that are not recognized whatsoever. So down here, this is actually in front of Orion, but it links in with the stars in Taurus through these low density connections. So what we're doing here is we're identifying significant networks of stars that link young populations. And this gives us a lot of opportunity to understand how star formation passes between these regions. And we'll get more into that in a minute. But before we do, I'll just briefly show you Orion here. So you guys probably know the well-known parts of the Orion complex pretty well. So Orion Nebula is here, Horsehead, M78, etc. These are all parts of the Orion complex. Now, in our study, we only check out to about 333 parsecs. That's because it's parallax of 3. That's why it's 333. But you can see that, so the outer edge of Orion, as it's been previously known, only goes out to about here in this chart. So this is once again the looking down from above the galaxy image. So you can see that we have a few groups recognized here, but most of what we see is way closer to the sun. And also not even close to the populations that are known here. So, Orion is here. We only find like 2 stars there. That is the Orion Nebula. Same idea with the Horsehead. We do find a little bit of an overdensity around the Orion's belt, which is another site where young populations are known. But most of it is well outside of that. So we're seeing this large extension to group 1s. This is that yellow population. Then we've got group 3, which we are able to link directly with Greater Orion. So it was recognized as part of a large survey last year, but hasn't been linked to Orion before. So we're the first ones to do that. And this group 2 here is also entirely new. And it's pretty big, and it extends massively in the direction of the sun. So we have these incredible large populations that we're recognizing that extend far beyond what's ever been known before in these regions by hundreds of parsecs. So this is like 300 or so light years. So we're expanding these populations in quite a dramatic way. All right. So now for what I think is the most fun of these regions. So this is Sco-Cen. So Sco-Cen is sort of the big daddy of the populations that I've been studying here. And this is the old picture of it. So once again, this is in galactic coordinates. So galactic equator is here. This is basically the Rho-Ophiuchi complex. So it's called Upper Scorpius in association talk. So this is basically the same sort of location where all these reflection nebulae and all that stuff around Antares and Rho-Ophiuchi. That's what you're seeing here. And then there's more out in this direction. So Lupus is in here somewhere. And then Crux is right there, along with the Coalsack Nebula and that whole complex. So now that you're more or less oriented here, the traditional view of Sco-Cen has been that it divides into 3 broad subregions. So you got Upper Sco here, which is the densest and the youngest of them. You've got Upper Centaurus Lupus, which contains Lupus and some other older populations. And then you've got Lower Centaurus Crux, excuse me, which is sort of in between the two in terms of age and extends farther towards some of the complexes in Chameleon in that region. So keep this in your mind. And now let's have a look at my Sco-Cen. So the boxes are the same. I haven't changed anything about the boxes that I'm including here, but you can see that my stars aren't really respecting the borders very well. They go far beyond them, and in quite dramatic cases in some varieties. So let's start over here. So this goes in the direction of the open cluster IC2602. Some of you guys might know that if you've done observing in the southern hemisphere, but these are clusters that have occasionally been recognized as part of Sco-Cen, but there haven't ever been really links that have like directly brought them in. While we are finding the low density extensions, it does appear that they might be a little bit more removed from Sco-Cen than the rest of the populations we see here, but it certainly looks like there is a link between Sco-Cen and these clusters in what I call the IC2602 branch. But there's also stuff down here. So these two clusters here and here, these make up part of the chameleon complex. So this here is Eta chameleontis, and this is Eta chameleontis, and this is Epsilon chameleontis. And these both serve as a clear extension of the LCC group. And then let's go over here. Now, what's this? This is the Chronostralis Association. Now, this has been a recognized association for quite a while. It's been recognized as likely associated with Sco-Cen because of the fact that it has very similar motions. But in our observations, we find this very clear bridge that connects structures in mainly in Upper Centaurus lupus, which is this area here, and it brings it directly down into Chronostralis. Okay, so this is what happens when we use our subclustering on this region. And you can see that we pick out all of these structures strewn all around Sco-Cen, including some that are in this new region that we recognize towards Chronostralis, and the groups I mentioned in towards the XC2602 branch. Now, it's worth mentioning that Upper Sco and Lower Centaurus Crux do appear to have a real structure in the sky, although we don't actually recognize any sort of like top-level cluster in Upper Centaurus lupus. So, you know, it's a bit of a matter of nomenclature, whether or not you want to recognize Upper Centaurus lupus as a real structure or not. But it looks like, in our case, we're finding it to be quite a bit more fragmented than has been suggested in the past. Now, this is where things get really interesting. And this is looking at ages. So the color bar is set up so that the youngest stars are in purple, or I guess black, and the oldest stars are in yellow. And it turns out that all of the oldest stars in the association follow this arc here. So what I'm doing with these contours are all basically, they're contours that represent where the clusters were in the previous diagram. And what I'm doing is I'm color coding them by age. So in green and blue, we have stars that are older than 20 million years old. And in red, we have all others. And we can see that all but two of these follow this incredibly clear arc in the plane of the galaxy. So it's this semicircular thing here. And we're calling this the Libra Centaurus arc, because it appears to be like this origin point for star formation in the region of Sco-Cen. Now, arcs are an interesting structure in astronomy because they comprise a portion of a sphere. So you can imagine, okay, what processes might be spherical that might cause a star formation event to occur? Well, that brings us to what's called triggered star formation. And let me just briefly play this video here. And you'll see how this sort of works and how you might expect there to be an arc-type structure in Sco-Cen. So let's say we got a very large molecular cloud, and we've got a star about to go supernova right next to it. So this is from Caltech Explore Astro. So supernova goes off, hits the cloud, compresses the gas, and stars begin to form along an arc, just like that. Now, this is a great way to trigger star formation simultaneously across a large area using some sort of external input. And that appears to be most likely what's happening in Sco-Cen. So, oh, it's going again. Yeah, I need to pause it and then, yeah, there we go. That appears to be what's happening in Sco-Cen. So if you sort of just look at this diagram here, put a supernova right there, you can sort of imagine how this ties into the diagram in that, supernova collides with a cloud, it compresses it, and that compression causes overdensities to appear that can eventually collapse to form new stars. So that's our explanation currently for the origin and star formation in Sco-Cen. But things start getting increasingly interesting when you look at the progression of star formation away from that original arc. And you can see here that you see things get increasingly purple as you go down away from the arc. And this happens in quite a few directions. So right there, and then if you go in the top-down view of the galaxy, in this direction, there, and once again here, although because we're looking top-down, it's not as easy to see that one. So the question is, how could that happen? What mechanism could cause this smooth gradient of ages across a region? And what appears to be the answer is a mechanism called sequential star formation. So this is just a close-up on one of those regions that has a very clear gradient. This is taking a close-up on LCC. So you can see there's our cluster on the Hdbscan arc at the top, and then younger, and very young. So it seems to be very clear, this trend. Now, this brings us to sequential star formation. And the idea behind this is when stars are formed in a dense cloud, and that cloud is done forming stars, what happens is radiation from those stars goes out and it radiates out into the cloud. And what happens when this radiation collides with the surrounding cloud is it compresses it, similar to the supernova that I mentioned before, but on a smaller scale. And what happens is that compression can then cause more stars to form. And then that happens again, compression, more stars form. That happens again, compression, more stars form. So you can sort of see you get this sort of like propagating wave of stars just flying across Sco-Cen here. That appears to be what's happening in this case, is you have just this slow burn of star formation, just slowly working its way across Sco-Cen for approximately 15 million years.
Kind of sounds like dominoes falling over.
Yeah, kind of. That's sort of the idea. Yeah, is that, yeah, when one event happens, it prompts another to occur, and so on and so forth. So yeah, exactly like dominoes. So it turns out this is actually consistent enough in its speed that we can actually plot this age as a function of distance. And to our knowledge, this is the first time this has ever been done on any association ever. And you can see, so on the bottom axis here, this is distance from the arc of old stars that we discovered earlier on, the one that we think was likely formed by a triggered star formation event from a supernova. And then on the vertical axis, we have the difference in age between that group and the Hdbscan arc. And as you can see, the farther you get away from the arc, the younger you get. And it turns out there's actually a very consistent speed for this, and it's about 4 kilometers per second. So we can't really contextualize this yet because not a lot of modeling has been done on these scales. But it's the sort of thing that's going to be great for us to to like test against when we finally get these models out, because there are a lot of different mechanisms that have been proposed as having effects on sequential star formation. And yeah, these include things like something posed by a collaborator of mine, Stella Offner, and that is the injection of what's called turbulence into the cloud ahead of a star formation event to sort of like infiltrate it from behind and cause star formation behind it. It's an interesting mechanism that will probably make a little bit more sense when I get into turbulent star formation properly in a few minutes. But the bottom line is that having this known speed for a sequential star formation event will allow us to compare to models later on and understand what processes are dominant in causing this propagation of star formation. Okay, so now for Perseus. So this one's a little bit less flashy in that it doesn't have nearly as much going on in it. So there's only 2 groups. One of them contains the open cluster IC348, and one contains another open cluster, NGC 1333. But both of these have this big extension out towards the east that has not been fully recognized in previous work. Now, it looks like they don't really, they seem to overlap a lot in on sky coordinates, but they do have more of a clear division in velocity here. So you can see they do appear to form like two very distinct clumps in velocity, which seems to indicate that they were formed from, somewhat different clouds. So now the interesting part about this is what happens when you look at it in ages. So let's pull up the age map for this. So it's a little bizarre, come to think of it, because here are IC 348 and NGC 1333, and you can see that they're black. So they are basically the youngest stars that we find in our populations. But next to them, we have this older population, which based on our estimates for the group ages is about 17 million years old. So what appears to have happened is we have two distinctly different groups in velocity. They have both caused star formation, it's dispersed, but then somehow it's happened again. And that might not sound too bizarre, but it actually kind of is. The reason for this being incredibly bizarre is that normally what happens in star formation is, stars form, and then after the stars are done forming, the radiation from that event disperses the gas. And if there's no more gas to form stars, it's going to just disperse, and that's going to be the end of things. If there's more gas nearby, it'll probably continue later on. But that's not what we're seeing here. We're seeing like a discontinuous effect. We're seeing burst, nothing, burst in star formation. So this is bizarre because that shouldn't be able to happen if you have a static gas cloud. If stars disperse, or if the cloud disperses, you can't make stars anymore. So what's happening here? And the working idea that we have is that there have been bursts caused by gas flows that inject material into these clusters. So if you imagine you've got this cluster that's forming, it disperses its gas, but there's still gas infalling, still gas being fed to the system from outside. So what ends up happening is that you get this gas flow colliding with the dispersing material and the radiation from that previous event. And what ends up happening is that the gas can sort of like find a new location to set up an equilibrium, and it can begin forming where those flows meet. That is the flow from the radiation from the old cluster and from the gas flow coming in. And this is something that actually has not been modeled before. It was sort of fun having a conversation with my collaborators on this, and that they basically just said, yeah, we haven't really thought of this until now. It's cool that it's coming up. So it's the sort of thing that's going to be likely brought up in new simulations soon. But it does look as if there are ways for star formation events to essentially momentarily pause their continuation until flows can bring enough gas back to the region for star formation to then begin again after that. And it looks like this happens in Taurus as well. So I mentioned that there are a lot of groups, old and young, in Taurus. This sort of could explain the fact that we have clusters that look like they're connected, but seem to be all over the place in terms of space and in terms of formation time. So this could actually be a very common process that just hasn't been explored yet. Okay, and now for the last of my spotlights on some interesting processes that come up in my research. So this is focusing on 4 very dispersed groups, and none of these were known of 2 years ago. These are all brand new associations. A lot of them probably haven't made it into a presentation ever before. So let's have a look at them. So just to go over some basic summary information on these. So these all have a lot of things in common. So they are very sparse. So you can sort of look at the densities here. So this one here has almost 170 stars, and you can see the scale. This is 140 parsecs by 140, well, yeah, 140-ish parsecs. So this is a massive scale. And 140 squared is big, much bigger than 168. So this is like a low star density, very, very low. In fact, this particular region here is what I was pointing my field at in that original diagram where I showed what the result of sparse star formation was. So So yeah, they're very sparse regions, but what's also important is that they're also very similar in age, bizarrely. So in this one here, all of these subgroups, regardless of how far away they are from each other, they're all almost exactly 25 million years old. Here, they're 33. Here, they're about 34, and here they're about 26. So somehow we've had multiple locations where stars on a scale of 150 parsecs have basically spontaneously just been like, okay, let's all form now. And that's sort of bizarre because, signals in space, unless it's like a supernova or something, don't normally travel that quickly. So it's sort of a question of how this sort of thing is able to happen. And the answer sort of comes down to we don't really know. But what we can establish is some details about how what the environment is like in these regions. So what I'll do is I'll explain to you what I alluded to a while back, and that's what's called a turbulent star formation. So here's my diagram of Carina Musca down in the bottom right corner. And you can see a few things. So first of all, the velocities are very similar. And you might expect that in such a big region, you'd have velocities strewn all over the place. In this case, no, actually. They seem to be very, very tight. And what that's often indicative of is that there are very weak gravitational interactions. Because if there are gravitational interactions, what happens is, stars find somewhat of an orbital speed to keep equilibrium with their parent cluster. Here, they seem to be just basically sitting still and not doing anything. And that sort of is reflected in the structure that you see. So I mentioned that this is a 33 million year old cluster or association. And over 33 million years, if there's a lot of gravitational interaction happening, you should not see structure. That structure should have been smoothed out. It should basically be a featureless cloud at this point. But what you see instead is, look at all these lines. There's one here. There's one here. You can sort of make out this big network of these long strings of stars that go across this entire region. And what this says to you is that there has been very little in terms of interactions to destroy any structure that originally exists. So we basically have filaments of stars that have just stayed there from the time of formation. And it turns out that when you have star formation that happens in filaments in these very sparse environments, it's often the case that what's called turbulent star formation is taking place. And that is when gravity has very little effect on anything. And that might sound very bizarre when you're talking about things collapsing in space, that gravity doesn't really have an effect. But it turns out that's exactly the case. So this is actually where some of the research that I did back in Victoria comes into play. And that is that we looked at 3 different regions where we have star formation taking place. And what we did was we took a look at the different mechanisms, the different forces that are causing binding. And in the more massive regions, so for example, the region in Ophiuchus we looked at, we found that gravity is important. It has a binding effect to cause stars to cause these cores to collapse. But in Taurus, we found that there is, it's highly dominated by just random motions in the cloud. So you can sort of imagine this you just have all these random motions in a cloud, and then you have little pockets of it where the gases calm down and taken somewhat of a more calm demeanor. And what ends up happening is that the turbulent motions are able to basically corral the gas from this quiescent region, this region where there isn't a lot of turbulence, and cause it to collapse just by the turbulent motions alone, just pressing on this bunch of gas. So that appears to be what's happening here based on the absence of gravitational binding. Now, how could this happen so rapidly? This is where we're going to need more modeling, and I'm going to have to talk to some theorists to try to get some ideas as to how this could happen. But it's unclear whether this could happen spontaneously. It's likely that this would require some sort of like larger input of energy to cause it to happen rapidly. So this could be a very distant supernova to just give it a little bit of a jostle to just get the turbulence to start flowing, or maybe a spiral density wave. So these are basically overdensities that are brought on by just motions in the galaxy that that manifest and can possibly cause star formation on a large scale. We don't really know at this point, but that's sort of what a lot of this is coming down to is, you know, we're just coming with a whole bunch of pilot ideas that we're hopefully going to be looking into more in the very near future. Now, I haven't even gotten into these. I'm just putting them up there. They seem to be interesting. We find new populations. We haven't really decided what to do with them yet, but stay tuned. So this is Perseus OB3. This is the Alpha Persei cluster. And here is the like more distant section of Chameleon. So both of them we find as being distinct groups with lots of independent structure. All right. So that's basically where my research is at right now. So I'm going to briefly go over some of the goals that we have in the future, some of the new bits of research that we want to explore. So first of all, looking at like large scale structures. So you may have imagined when you first looked at my work here is that it looks like there's like some bigger structure here, right? You know, it looks like there's like some long branch on this side, a long branch on this side. Maybe there's like another eddy to it there. It looks like this connects to something bigger, that it isn't just disparate groups of stars that are forming in isolation. There's some larger structure to it. And this is something that I was hoping I'd be able to get done for you guys before the talk, but it was a pretty busy time. So unfortunately, you didn't get around to that. But what we want to do is we want to try to connect the groups that we find in our current population to larger scales. And that would be by basically expanding our search radius of Gaia stars and, you know, looking farther out, looking deeper into space. Now, there's already been some progress on doing this. This has not been from me. So this is from a team at Harvard, I believe. And what they've done is they've done like a similar like large scale structure view to what I've done, but they've done it in terms of gas, not stars. And they've revealed what's called the Radcliff Wave, which is this long extended wavy structure of gas that extends out for you know, over a kiloparsec, so like 3,000 or so light years, if you prefer to work in those units. This is about a 3-to-1 conversion. So it would be nice to do a similar investigation to what they've done, but on stars, and also to see, you know, whether our version of the Radcliff Wave is sort of like offset. And because of the fact that we have all of these very like all these very small associations that often have not been recognized previously, we may be able to identify quite a bit more substructure. And that could allow us to identify new patterns that emerge out of star formation within the local area of the galaxy. Okay, and lastly is exoplanets. So this is not my personal department, but it's something that a lot of people that are in my research group have a lot of interest in. And it just so happens that we got somewhat lucky with the populations that we found, and that is that it turns out that one of them is in what's called Tessa's continuous viewing zone. So this is a spacecraft that's surveying bright stars for planets, and is basically going to be spending about a year just staring at a portion that overlaps with one of my associations. So if there's something there, we're probably going to know about it and know about it pretty soon. But essentially, the reason that finding planets in young populations is important is because when we see a planetary system in a young association or a young cluster, we know exactly where it came from, because based on the density of that region, we're able to like gather like how many interactions it's had with other stars nearby. We can gather whether it's from like an Orion type situation or a Taurus type situation. We understand the environment that it came from. And this is where I can sort of like draw it back to the sort of like Bayesian approach that I mentioned before, and that is that, well, the properties that we know about the sun are, we know the orientation of planets in the solar system, but we don't know where it came from. And then if we look out in space and we see, okay, well, we've got this population of planets, we know their planetary system layouts, and we know where they're from. You can use that statistics to gather a model as to what the odds are that the sun was in X situation versus Y situation. So that's going to be something that's going to be developed by most likely other people in my research group over the coming years. All right, let's go over some conclusions here then. So nearly all groups that we identified in the solar neighborhood have lower density extensions. We find about a dozen clusters that have little to no coverage in literature. In Sco-Cen, we find an arc of old stars that appears to represent an origin for star formation in Sco-Cen, with stars that are further from the structure having progressively younger ages, likely indicative of sequential star formation. In Perseus, we find repeated bursts of star formation, suggesting a resumption of star formation after gas dispersal. We find a few new associations with evidence of turbulence-driven star formation. And in the future, we hope to expand into large-scale structure and planetary statistics. Okay, well, thank you very much for listening. I'd be happy to take questions now. You've been a great audience. Yeah, feel free to ask questions.
Yes, sir. I had a question formed in my head as soon as you brought it up.
Yes, sir.
You mentioned early on that stars, when they first form, they're a little bigger in size and they're brighter, but their temperature is pretty much the same. So there's not a lot of change there, but it's not enough of a recognizable, measurable difference for you to use it to really tell their ages. So you obviously use this method here, which it looks like you're using the context, very much like you'd use the context of a word in a sentence that you don't understand to help infer more about it. So my question is, going back into the composition of the star itself, why are they brighter when they first form versus a certain portion of their age, and is that fairly consistent along the spectrum of stars?
Yeah, so basically what ends up happening is that the outer envelopes of the stars, as gravity sort of pulls on these stars, it's not in equilibrium yet when it's still in the process of formation. It's still contracting. It still has this large envelope that is, it's still going to be, undergoing fusion processes, but it's going to be quite a bit farther out. And, when you're dealing with luminosity relates directly to the area over which it's being emitted. And it turns out for these stars, it's actually a big difference, like many orders of magnitude difference. So the effect is quite large, and it's something that you can measure quite well. Now, there is absolutely a temperature difference that does exist, but it's sort of dependent on the star that you're looking at. So you can sort of see that on this diagram here, right? So I'm looking mainly at stars that are fainter than the sun, which is why I was able to say the temperature stays kind of the same. But so you can see here for our red dwarf, it drops straight down. So it only contracts, temperature is constant. But for the sun, it contracts, then it heats up, and then it contracts again. It turns out the physics behind this is rather complicated. I'm not sure I'm especially prepared to make that explanation right now. But yeah, there's a lot of gas dynamics and physics that goes into making these stellar models. Not really my area of expertise, but if you want to look into it, there's some great resources that I could probably point you to if you want to learn more.
Well, thank you. It makes perfect sense in terms of the way you've described it. And just as a side note, I'm kind of guessing that the composition as the minerals are cooked down and the fusion process take place and the alterations take place in the stars, that probably has something to do with how they contract and some of their temperature as they age as well.
Yeah, to a degree. So there's a lot to do with opacity. So that is, as the internal makeup of a star or the internal structure of a star changes, you get different sources of opacity. So like, H minus, for example, becoming increasingly dominant. And that can sort of like guide what the what the sort of like star formation progression is in these regions. Definitely something that I wish I could give you a bit of a better explanation than I am now, but it's basically those differences in opacity and the chemical reactions that take place that guide that sort of process.
Fair enough. Thank you, Ronan. That makes perfect sense. Obviously,
no worries.
there's not enough consistency to just look at a star and go, hey, it's about that old. You're having to do the mathematical algorithms that you're doing. So
yeah, exactly.
You're right. It's complex.
Oh, definitely, yeah. And metallicity, which is one of the things that goes into making these models, also significantly changes the location on this diagram by once again tweaking those opacities. So yeah, stellar astrophysics is kind of hard. But the nice thing about the method that we're using is that we sort of like take all of that into account. So obviously we do a lot of citing of models that are much smarter than I am in terms of putting together these data sets for, coming up with expectations for stellar luminosities based on intrinsic properties. And those all go into the assumption, into the models that we generate. So yeah. Thank you.
Very
Anybody
good.
else?
I have a question. What's the force behind turbulence? What is turbulence?
So that is kind of a good question. Okay, so basically, when you have gas that is being influenced by motions that are external, so often there is like an external driver to it. So you can have, like, for example, I mentioned that mechanism that was pioneered by one of the people on my grad committee, which is this idea where you have stars that emit outflows from their accreting surfaces. And what ends up happening is that these flows of gas collide into the surrounding ISM. And sort of in the same way that you like get buffeting of air around around your door as you open or something like that, is sort of the same idea, and that you get these these jostling flows of gas that that oscillate and create these sort of effects that that can cause momentary overdensity. So it's sort of best to think of it in that same sort of view as imagining it in terms of like the weather, where you have these processes that take place as inputs go into this fluid, and they jostle up gas, they cause these flows to go in different directions, they collide, they create all of these vortices. That's sort of the thing that we're dealing with is something comparable to that. I know that might be a little bit of a fluffy answer to some degree, but hopefully that sort of like gives you the idea behind how it works. A more detailed answer would go quite a bit more wholeheartedly into the fluid dynamics aspect, but going farther than that is not quite my area of expertise. So
Thank you.
I'll leave it there for now. All right, yeah, no problem.
Okay, I've got a couple of questions. First of all, let me just say that you really kind of opened my eyes to how many different drivers there are for star formation. It's like you described about a dozen confluences of circumstances that could cause stars to form. And what I'm, outside of the model, we kind of look at the most, like you started off with the Rosetta Nebula collapsing and forming, a cluster. The other one was a supernova compression, okay? But one you kept sort of mentioning but never got into in depth was the compression waves and spiral arms in the galaxy. And I've always thought that was also another leading contender for star formations that I'm not sure we know exactly why the spiral arms form. There seem to be, elements of magnetic fields that apply to that. But that my idea was that the leading edges of spiral arms tend to pile up.
Yeah.
Okay. So if you could talk about that, but back to the supernova for a minute. So in the Sco-Cen Association, where you showed the little movie about the compression by the supernova, I guess I'm having trouble with the scale on this, because those associations, in my mind, if I try to lay constellations over that, they're huge areas of the sky. And my question is, does a supernova really have an effect at that range? Well, I just did a quick search here and asked, what's the diameter of the Veil Nebula? And it turns out it's 100 light years. Okay, so I can see supernova having an effect out at a distance like that. But unless I've got the scale wrong, there must be hundreds of light years across these associations.
Yeah. So the scale of the Veil is, I suppose, comparable to these things. Now, the Veil is a supernova event that is, at an advanced stage, supernovae become completely dispersed, and the gas that you see is no longer there in any form. Now, in the case of Sco-Cen, you don't necessarily need for there to be like a lot of material that's still being emitted by a supernova to have it impact gas. All you need is the energy that comes with it. And supernovae are incredibly energetic events. So that means that you can get that energy with a relatively small amount of material. So even though that material might be diffuse and you might no longer see any of it, it's still going to be there, and it's still going to be imparting a lot of energy into any gas that it's interacting with. So you don't necessarily need to have the veil for a shock to have impact. You just need to have that leftover energy from that event rippling through the interstellar medium. And it turns out that can actually carry quite far and can have an effect very long after that formation.
And about the spiral arms and.
Yeah. So, oh yeah, sorry, go ahead.
Is my conception wrong about the leading edges of spiral arms being regions of star formation?
Yes, that's exactly correct. That's right. Yeah, so you get this buildup of star formation along these large scale waves. And this sort of ties in a little bit to what I showed you about the Radcliff Wave, and that you have this like large scale area where you have, gas buildup and young star buildup that happens over a very long distance. Now, it's not. Now, there are other things that go into that. So we do get this sort of like buildup of gas density on the leading edge of these spiral arms, but we also get some sort of like oscillations within them as well. So the Radcliff Wave, part of why it was so interesting was because of the fact that it oscillates. So let me just keep going down here. I've got a lot of slides.
There it is.
Yeah, there it is. Okay, cool. So you can sort of see it has this sort of like wavy structure to it, right? Mm-hmm. So this is something that I have not spent a lot of time thinking about. So this is the sort of thing where I probably just recommend that you go to the paper or the press release from the team that did this discovery and look at that for more information on it. But essentially, there are mechanisms that take place in shaping that density wave that can further sort of distort where the gas is during that process. So yeah, star formation has a lot of gas dynamics taking place in it, and that drives some rather interesting effects that show up. And it turns out that it's very common for people to not think about this when they're modeling. So that's why it's such an exciting thing to be an astronomer in, because it keeps being that I'm like, hey, look at this thing, isn't this weird? And I show it to my theorist friends, and they say, that's not supposed to happen. How is that happening? Okay, let's try to figure out more about that. So that's sort of where I'm like perpetually residing at the moment. Is I'm an observationalist first and foremost, right? So my job is to look up at the sky and try to find these neat things that have astrophysical implications to them. And it turns out that happens quite a bit. And in some ways we have an easier job than the people that are our theorist counterparts. So often the work that we do is going to have the effect of informing our theorist counterparts and, providing the impetus to try to study this new, weird, interesting thing that we found. All right, anybody else?
Okay, Ronan, well, we certainly appreciate the talk. I found it highly interesting, entertaining, and sounds like you're going to discover a lot of other interesting things. So,
That's the hope. Don't even have my master's yet. I'm only a second year.
yeah,
So I've
yeah.
got a long way to go.
All right.
Thank you very much for having me, though. This is a lot of fun. It's good talking to you guys.
Yeah, thank you so much.
So
Yeah,
we
no
got
worries.
we try to do clapping in these meetings, but we never can coordinate it enough. So, okay, I'm going to get up back to my what I call my Hollywood Square view here.
Yep, and I'll unshare my screen here. Feel free to ask me questions by email if you want, by the way. Just stop the share there. I can post it in the chat if you like, and if you have any more questions, I can answer them via email.
Okay.
There you go.
Thank you.
Yeah, no worries.
Just out to the group, if anybody had thought about any questions about the what the club's up to or some of the stuff we talked at the front of the meeting, if anybody has questions about that, we can spend a minute or two on it maybe. Okay. Tim, I see you joined us. Were you a little late?
Yeah, we were selling a house.
Oh, yeah. Okay. That's the way it goes. So everything on track?
And it looks like it. So far, we'll find out tomorrow morning.
Okay. Good luck.
Thank you. Just wondering, was there anything significant as far as voting that came up today?
Yeah, we actually had some interesting discussions about voting in terms of the fact that since we've been doing virtual meetings, we really can't vote the way bylaws are set out right now. And so there was some question about how can we modify things so that we can actually vote virtually. But it seems like we need to meet in person to establish that or to pull that up by the bootstraps.
That's the problem.
But it's a topic that several people expressed interest in just today. And so I think we are going to be discussing. What brought it up for you?
I'd seen some of the discussion go by on email and just wondered if it had been brought up.
Okay. I think it's something we'll be talking about with some direction here in the next couple of VC meetings.
Okay, no problem. Just checking in. Thank you.
Hey, maybe we can have an impromptu meeting out at Perseus at the theater there, and we can call it a Star Chamber meeting.
Well, it may very well be that our first get-together meeting might be an outdoor meeting like that. And yeah, that could be one way to handle it. So.
But it's good it's not this weekend.
Yeah, definitely not this weekend.
Come on, the current forecast for Monday is only 2 degrees.
Yeah. Wait till it's spring.
No, is that Celsius or Fahrenheit?
Cold winter for a reason, folks. Come on.
There's not enough scotch in my flask to go stand out in that.
So Don, I heard that Tom Weidman and family are actually camping at Copper Breaks this weekend.
I know. I need to hit them up and tell us what they thought.
They've been going there for many years, so they have indicated a lot of experience there, and they got run out by the weather. They bailed this morning.
Ah, okay.
Yeah, get home before it gets so bad they can't get home.
That was exactly the plan, and that really annoyed them because they wanted to do star party and astrophotography and such from out there, but they posted on Facebook this morning that there's too much wet coming with the cold, and they're afraid they're going to get out and they're not going to be able to travel home if things freeze up because it's even windier and colder up there than it is here.
Not much.
There are a lot of roads that have been closing down early, so if you have to go driving around this weekend, especially in Central Texas, please be safe.
Avoid that which is elevated. That's the dangerous stuff.
Yep.
Well, it was great talk, Ronan. Hopefully we can have you back as your research progresses and you can give us an update on how things may have changed and what else you've discovered.
Yeah, thank you very much. I'd be happy to. Hopefully I'll have some new results soon. I've got some observations on Sco-Cen taking place at a telescope in Australia in a few months. So the idea is to hopefully get some very detailed spectroscopy on some of these like follow-up observations on these candidate members that we found. We'll have about 1,400 of them that we can observe using the telescope. So it's a really, really wonderful instrument. Anglo-Australian Telescope has some of the best field spectrometers in the world. So that's going to be a great new experiment. And hopefully we'll get a good paper out about more detailed views of Sco-Cen then.
And what about Hdbscan? Does that, you guys taking advantage of those spectroscopes?
Mhm.
Yeah, so Hdbscan is being used a lot for Hdbscan, which is a galaxy survey, and also a lot of planet work is being done there. So for our purposes, it doesn't have quite the sort of it doesn't have the same like skill set to make it like specifically good for what we're doing. Now,
Okay.
what I have been doing is I've been using the 2.7 meter a lot. So I actually spent 6 nights in January on that telescope, basically just observing a whole bunch of objects that we've identified as part of the survey and trying to get follow-up spectroscopic information on them. So that is like find like alternative indicators of them actually being like really young objects. And also by getting information on their radial velocities, because Gaia only gives, well, it only gives good velocities that are perpendicular to the line of sight. So that is our transverse velocities.
Yeah.
But to get the full 3D motions, you need to have transverse and you need to have the radial.
Radial.
So that's going to be great for improving our view of the directions that these things are moving. And also, just to briefly call back to these discussions of how the chemical abundances change in stars. When stars are evolving, they actually burn through the element lithium very quickly as part of nuclear processes. And it turns out that the rate at which, the way in which lithium burns is basically when it hits a certain temperature in the star's core, it cycles through it incredibly quickly. So that means that, you know, you'll get in low mass stars that there's just this boundary where lithium just is no longer there because it's hit that temperature where lithium disappears. So what you can do is you can look for lithium, and, you know, if you look at enough stars, that boundary tells you like almost exactly what the age is within like a couple million years. So it's a really good way to get very precise age estimates. So that's going to be another thing coming up in the near future, likely with the Australian data. So yeah, that's that.
Okay. So we always have trouble ending these meetings.